This is a red blood cell, the primary carrier of oxygen in your blood. There are about 1.9 to 2.3 billion cells like this in your body. It's very pure. Excluding water, over 95% of it is hemoglobin. Each hemoglobin is a tetramer composed of two pairs of different globin peptide chains. One pair is the alpha globin chain, encoded by the HbA1 and HbA2 genes in the 13.3 region of the short arm of chromosome 16. Each of these genes can encode a functional alpha globin chain. Since your chromosomes come in pairs, you normally have 4 functional HbA genes to produce enough alpha globin chains. The other pair is the beta globin chain, encoded by HbB gene, located in the 15.4 region of the short arm of chromosome 11. Under normal conditions, there are 2 functional genes to produce enough beta globin chains. Your genes determine the equal expression of alpha and beta globin chains. This balance is key to the normal function of your hemoglobin. However, during inheritance and evolution, these genes can mutate, disrupting this balance and causing abnormal hemoglobin, such as point mutations, gene deletions, or gene duplications. These mutations cause an imbalance in the expression of alpha and beta globin genes, producing unstable hemoglobin, which leads to abnormal red blood cells and triggers anemia. Anemia caused by mutations in these 2 genes is known as globin synthesis imbalance anemia. Pathologically, it's divided into 2 types: alpha thalassemia and beta thalassemia, commonly referred to as alpha thal and beta thal. Alpha thal is mainly caused by gene deletions. The more HbA genes missing, the more severe the symptoms. Beta thal is primarily caused by single base mutations, and different mutations have varying impacts. There's also a special case, the co-inheritance of alpha thalassemia and beta thalassemia. If someone has alpha thal, the ratio of alpha chains to non-alpha chains drops. Naturally, the scale tips to one side, losing balance. But if they also have beta thal, the ratio of alpha to non-alpha chains rises, and the scale can actually regain its balance. In this way, the co-inheritance of alpha and beta thal allows globin chain synthesis to find a new balance, which also lessens the severity of the condition. Conversely, the more imbalanced the synthesis, the more abnormal the red blood cell shape and function. Of course, abnormal red blood cells aren't always a bad thing. As seen in this study from The Lancet, high incidence areas for thalassemia and malaria endemic regions overlap significantly. This is no coincidence. Extensive research shows that thalassemia patients have a natural immunity to malaria. Compared to normal cells, the mutated red blood cells of thalassemia patients are less likely to be infected by malaria parasites. Even if they are infected, the shortened lifespan of these cells doesn't give the parasites enough time to reproduce. Thus, carriers of the thalassemia gene were more likely to survive in malaria-prone environments. However, while we've ended malaria's 1,000-year history in China, the carrier rate for thalassemia in southern China remains high. Although most carriers are silent or have mild cases with no obvious symptoms, this also means couples unaware of their carrier status can easily have children with severe thalassemia without knowing it. So, prenatal screening for thalassemia is vital. Hematological analysis can confirm if both parents have it, while genetic testing can identify the specific type of thalassemia. Take the 3 most common silent mutations of alpha thalassemia in China's Hainan region as an example. On your test report, the genotype will be written in this format, which is actually not that hard to understand. For these 2 genotypes, alpha represents the HbA gene. The minus sign indicates a gene deletion, and 4.2 and 3.7 represent the length of that HbA gene deletion. And this represents the 369th base pair of the HbA2 gene. Compared to the reference sequence, the C at this position has been replaced by a G. There are many other mutant genotypes related to thalassemia. In the past, the only way to cure thalassemia was through a bone marrow transplant, which means transplanting healthy bone marrow into a patient to restore normal blood production. The problem is, transplants require a matching donor, and the surgical risks are quite high. Therefore, not every patient is a suitable candidate for a bone marrow transplant. Genetic diseases require genetic solutions. This sounds like science fiction, but gene therapy isn't that far off. In fact, we already have gene therapy methods for beta thalassemia today. Simply put, it involves extracting a patient's stem cells, repairing them with gene editing, and transplanting them back to help the patient regain relatively normal blood production. Currently, there are 2 main methods for this type of gene repair. One is using a viral vector to directly insert the beta globin gene into the patient's own stem cells. to help them produce beta globin chains and increase normal hemoglobin synthesis. An example is Zynteglo from Bluebird Bio in the United States. The other method is to directly intervene at specific gene sites in the patient's stem cells by increasing fetal hemoglobin gamma chain expression to compensate for the imbalanced beta globin synthesis. For instance, China's first case of severe thalassemia successfully cured by gene editing, and the clinical trials for severe thalassemia gene therapy by BGI and Shenzhen Children's Hospital. While these treatments are currently either too expensive or still in the clinical trial phase. With the growth of genomics and the maturation of technology, costs are expected to drop. Genetic testing is a perfect example of this trend. On May 31st, 2007, American biologist James Watson had a genetic test done. The sequencing alone took 3 months and cost over $1 million. Now, for just a few $100, you can get your report in a single week. In the future, gene therapy and testing might truly be accessible to everyone who needs them. Well, that's all for this episode. Thanks so much for your likes and follows. See you next time.